In this problem, there's a bat and it is sending out sound waves to an object that's moving away from it. Now the bat is at rest and the object, whatever it is moving away from it at 27.5 meters per second. Now when the bat sends out the waves, because this thing is moving away, the frequency that that this object is going to receive the waves at is going to be adjusted based on the relative motion between the bat and the object. This is called the Doppler effect. The Doppler effect just being an apparent change in frequency when the source, which is the bat, and the observer, which is the object, have different speed, or have a speed, right? Yeah, have different velocities basically. So the trick about this problem is there's a sound wave moving from the bat towards the object, but then there's going to be a sound wave bouncing off of the object going back to the bat. So what we're going to have to actually do is do this Doppler effect equation twice, once to see what the frequency that the object receives, and then again to see what the bat gets back. So let's go ahead and do that. Now this equation, I'll write it out for you, or I'll break it down for you. The f prime here is the apparent frequency, or the frequency that's observed. The v here is the speed of sound, which is 343 meters per second in air. That's given in the textbook. V0, or VO, I guess, actually, is the observer's velocity. In this case, it's going to be 27.5. And then speed again of speed of sound, and then the speed of the source, which is, this time the source is going to be the bat, which is not moving at all. And then F is the regular frequency, the frequency that was emitted. So let's go ahead and plug this in to find out we're looking for what the frequency is that the observer is receiving. So we have 343, and before I put plus or minus, let's just think conceptually if this frequency is going to be higher or lower. If we're sending out waves and we're moving away from those waves, we're going to be receiving those wave crests at a lower frequency than they're actually being emitted. So what that means is the frequency should actually be lower. And if the frequency is lower, that means that the numerator needs to be lower than the denominator. So we're actually going to put a minus sign instead of a plus. These should actually be plus or minus, and you have to kind of decide if they're plus or minus. Now in this case they're moving away, so we'll just say it's going to be minus so that this can be a smaller number than this, and that means that the apparent frequency will be lower. So we're going to subtract the 27.5, which is the speed of the observer, and then we have 343 plus 0 because the bat, which is the source of the sound, is not moving at all, and then that's times 50,000 hertz. And the reason why it's 50,000 is because it's kilo, and kilo is times 10 to the 3. So that's 50, oh I'm sorry, it's not, yeah, 50,000, that's right. So now we'll plug this into the calculator. So I have 343 minus 27.5, and that's divided by 343, and then we multiply that whole thing by 50,000, and we get an apparent frequency of 45,991 approximately, and that's in hertz. Now that is not the final answer. This is the frequency that is basically bouncing off of the observer. So what's going to happen is, or this object, what's going to happen is now we're going to flip it. So now this will be the source, and then the bat will be the receiver, or the observer, and now we're looking at this new frequency, which is 45,991, and we want to know what is the frequency that the bat receives back. So we're going to do the same thing. So f prime is equal to 343 minus the it's the observer's speed. Now the observer is 0, right? Because the bat, or plus or minus, but it doesn't matter because it's 0. the bat's not moving. And then we have 343, and now we have to decide again, plus or minus. Again, we're moving away, so that means that these wave crests are going to hit the bat at a smaller frequency, less frequently. So that means that this has to be a bigger denominator. So again, we're going to add 27.5, and that's times this new frequency, which is 45,991. So we're going to do this now. So 343 divided by 343 plus 27.5, and I get a final frequency that the bat receives as 42,578 hertz, but because they gave us, we'll say 3 sig figs, let's go ahead and put that into 3 sig figs, which would be 42,600 hertz, or in scientific notation 4.26 times 10 to the 4 hertz. All right, there's your answer.